everybody. Once again, I'd like to welcome you all for this second session of our international workshop on liquefiable soils. We have two keynotes in this session, keynote speeches, one at the beginning and one at the end. And in between, we'll have three presentations. I'd like to welcome Professor Robb to give the first keynote speech of this second section with a round of applause. Professor Robb is a professor at the California Polytechnic State University. He took his PhD degree on geotechnical earthquake engineering from the University of California, Berkeley, and in the past 20 years he has been researching and consulting on various extensive amounts of research projects on flow failures, residual strength of liquefiable materials, reliability, risk and reliability within seismic design and earthquake effects, dynamic earth pressures for basements and retaining walls, probabilistic fault displacement hazard analysis and seismic hazard analysis, and many more. I'd like to also thank him for his keynote speech.
Thank you. I want to thank the organizing committee for inviting me. This is a great way to end the summer. I start teaching classes on Monday, and my plane's going to land Sunday night, sometime around 10 o'clock, and then my first class is 8 a.m. on Monday morning. So I warned my students, but this is a great way to end the summer with, with a bang. I usually, when I talk about liquefaction, I'm usually talking about CPT, but I'm going to be talking about Shear velocity this time. And I want to explain why. First, I'm going to define Shear velocity. It's fairly straightforward. Right, we're talking about the speed of a vertically propagating horizontal shear wave. And in the geotechnical realm, we're usually in the range of 100 to 300 meters per second. The seismologists usually like to deal with slowness. I think that was a fad for a while, about a decade ago, and then slowness went away and went back to talking about shear velocity. The beauty of shear velocity is that there is almost perfect fidelity between lab testing and field testing. And look at this equation. In geotechnical engineering, we rarely have equations that are both exact and this simple. Right? Usually in geotechnical engineering, we have an equation and there's some physics, and then there's there's kind of a fudge factor in there, some semi-empirical coefficient in there. This is it, right? The small strain stiffness is equal to the density times the Shear velocity squared. And it has a lot of applications when we're talking about liquefaction engineering, and that's what I'm going to be going through. So I'm going to be talking about the applications that I deal with and that I've seen, and then I want to talk about measurements from small lab scale all the way up to field scale. So here's my cute little slide that I like to use for when I'm teaching liquefaction, and this has my PowerPoint graphics. So, right, you take dry, loose sand and you shake it, and it densifies. And then if we had fluid in there and we shake it fast enough, we tend to lose that particle-to-particle interaction and get liquefaction. And we have reduced strength and excess pore pressures. One of the things that I often do is I travel a lot for earthquake reconnaissance trips. I'm part of, if you've heard of Shear, I get to travel and gather perishable data so that we can incorporate that into our future design. Here's some pictures from Chile, where we had lateral spreading, and then we also had buoyant features that came out of the ground. And so the first obvious application is looking at liquefaction triggering. And here's some work that I and a bunch of colleagues, including Professor Chetton, worked on. And we're trying to come up with a threshold between non-liquefaction and liquefaction. And this is solely based on Shear velocity. Now, it turns out that this triggering method is not as accurate as CPT. CPT triggering methods are more accurate, but it's often cheaper and easier to measure show wave velocity. And measuring show wave velocity is very complementary to doing, if you're doing CPT, you can do seismic CPT, or if you're doing SPT, you have show wave velocity measured as well. The smaller inset figure is comparing our method to prior methods. So a few comments about the triggering method with show wave velocity. This figure shows that show wave velocity is not very sensitive to Planck's content. So you can see that Planck's content is not a predictor variable here. So that can be difficult if you're trying to figure out if something is liquefiable, if you're trying to figure out susceptibility. But show wave velocity is particularly good at aging. So if we're looking at aged soils, or if we're comparing man-made soils versus natural soils, show wave velocity tends to pick that up quite easily. And there's some follow-on studies that I'm going to touch on there. And as I mentioned, it's very complementary to measure. How common is it to measure show wave velocity when you're doing CPT work in Turkey? Andre, this is a question for you.
CPT is definitely becoming popular.
And when you do CPT, you also do seismic?
20% of CPTs are seismic, give or take 5%.
Did I do a good job with the
That's pretty good. Is there would the audience agree with that? Is there common movement towards measuring both tip resistance, sleeve resistance, and show wave velocity in Turkey? Not
Shear
separate. Yeah.
But also, you know, downhole,
Yeah,
etc. So,
yeah.
as geophysical method, it's quite common, but not necessarily as.
So a specific show wave velocity aging application is this method by Hayat and Andrus. And what they did is they went around and they measured show wave velocity in aged soils that had liquefied, and fresh soils that had liquefied, and aged soils that hadn't liquefied, fresh soils that hadn't liquefied, and came up with a correction factor. And this works pretty well, and is actually applied throughout the U.S., mainly by Department of Transportation officials when they're doing bridge siding and other construction in liquefiable areas. A separate study, and this was a colleague and I, where we combined the CPT and show wave velocity into one predictor parameter, and also found that it was really good at picking up aging. And we came up with this correction factor called Kg. And older soils have higher show wave velocity, higher small strain stiffness, higher cyclic resistance. And kind of a vote of confidence there is that Peter Robertson, who is Mr. CPT, has since adopted it for all of his methods. And so this has a lot of promise, and we're hoping to continue to develop this method where you're measuring CPT, you're also measuring show wave velocity at the same site. You join the two parameters as a predictor, and not only do you get some type of triggering prediction, but also you can detect aging quite well. A separate study that I worked on with Ricardo Dobry, we looked specifically at man-made or artificial soils, hydraulic fills and the like, versus naturally deposited liquefiable soils, and we found that we could pick that up with show wave velocity as well. And then this was a recent study, so this is liquefaction, but this is from a different perspective. This is for debris flows. And a debris flow is a liquefied material. The triggering is completely different. It's often rainfall induced, or there could be some other inducement. But then once it starts flowing, you get to that steady state behavior. And with this study that we just finished, we found that joy velocity in terms of VS30 was a good predictor and could easily replace a rather cantankerous predictor variable that the USGS had been using for years. So those are some applications that that I use and I see other practitioners using when we're talking about liquefied material. And what I want to touch on here is measurements. So again, the point of my talk is that joy velocity has perfect fidelity from the lab to the field. If you're doing, we've been talking about lab tests, and how do you get a lab test to correlate to SPT or CPT? You often have to say, well, here's the relative density, and then that relative density relates to this tip resistance or this penetration resistance. So there's that empirical gap that's in there. Whereas when we measure this in the lab, we can also measure joy velocity in the field one-to-one. So let's start out at small scale. We're doing small samples. We're doing cyclic triacs or simple shear, and we want to capture the small strain stiffness. We often stick Fender elements or piezo crystals in there. And an example from my lab is here I have a simple shear device, and I have the ultrasonic platens. And that works great for at the beginning of the test. You can measure it during the test. I have not been able to successfully capture joy velocity while it's liquefied. That's one of my goals. My long-term goals is to capture the joy velocity while the material is liquefied. And then after the test, we measure joy velocity equally. The ultrasonic platens have very high frequency, and so those waves don't really transmit through liquefied material. The second one that I'm going to show is a medium scale. I had this old data acquisition system. It was about 25 years old. It was great. We had all these accelerometers and pore pressure transducers and displacement pods, and you name it. We had it hooked up. We had pressure sensors, and we had been limping it along for 20, 25 years. And finally, we can no longer get the computers that the buses hook up to. We were ordering from China, and there's no longer any scrap computers left that we can. So my lab colleague and I built this data acquisition system, and we're rather proud of it. This was about $4,000. We have this National Instruments, we have 2 accelerometers, we have 2 pore pressure transducers that are hooked up to the load cell. I think we have 12 channels on this. And then he created this nifty little box. And what we're using this for is we're doing medium scale. These are essentially slump tests, but we're doing debris flow slump tests here. And we're looking at capturing both the deformation characteristics. So are we able to predict the deformation based on parameters before the flow happens? And then we also want to capture the strength of the liquefied material or the liquefied debris flow. This is version 1. That's why it's in a kiddie bowl. We're going to move to version 2 pretty soon. When we, I want to show you some large scale lab tests. So this is in my shake table lab, and this is a full size simple shear test. That bucket, we're doing simple shear. The white straps are Kevlar straps, and they're mimicking wire reinforced membrane. And I have a cute little video for you. Before I get to that, we have accelerometer arrays and pore pressure arrays in there. And here I'm showing an example of one of our sealed accelerometers. Here was a successful test. Note that sample creation for this is usually about 3 weeks to a month, as opposed to one of our earlier speakers where they could create a sample in about 30 minutes. It's already liquefied. I don't know if you saw that bulge at the bottom. This is a 0.2 CSR, 30 cycles. And that noise that you heard was we were pulling a T-bar through the liquefied material while it was liquefied so that we could measure the strength of the material in that liquefied state. That was 2 master students and several years in the making to try to get to that stage. So here I'm showing on the right a shear wave velocity profile before and after. Before is the solid line, after is the red dotted line. And we can see void ratio redistribution, which is really hard to capture in small scale lab. It's hard to capture in the centrifuge. You can see that we had loosening in this range and we had stiffening in this range. We also did CPT before and after. We could see void ratio redistribution there. And then, as I mentioned, this is just a little sidebar. Here we pulled a T-bar through, and you can characterize the strength based on the flow around this T-bar. And this matched really well with existing predictive methods for coming up with the liquefied strength for flow failures. So this is one of the things that I'm after, is that liquefied strength. I find it fascinating in trying to capture its deformation properties and its strength properties. Okay, so then we get to field scale. So we have invasive and non-invasive shear wave velocity methods. I'm going to talk a little bit about accuracy and precision. And the invasive methods are usually winners when it comes to accuracy and precision. But doing seismic CPT, you have to mobilize a truck, it costs a lot of money. Doing non-invasive methods is really easy. You throw out some geophones and either you make noise or you don't, or you capture the passive noise, and then the trick is in the post-processing. So, right, we've got refraction and reflection. Geotechnically, usually refraction is used for capturing the water table or some boundary. Reflection is not really used. It turns out that body waves are the small component when we're doing small sources, and it's the surface waves that are the big ones that we like to capture. So surface wave testing is what we essentially all use now. MASW, SSW, REMI, Blue, SPAC, FK, H/V, and I'm going to talk a little bit about DOS as well. So I'm sure a lot of you are aware of this, but Rayleigh waves are dispersive, and so different frequencies sample different volumes of material, and that gives us a good way of figuring out what the material properties are, or the small strain stiffnesses for different depths. And so this is all, this was all worked out years ago and has gradually been adopted into practice. The early concept is what they call steady state. You set up one frequency and then you set the geophones apart so you're picking up the peaks. And then you say, okay, that's the depth that I'm sampling. And then you set up a different frequency and do that again and again. And essentially SASW and MASW are just automated steady state methods. Here we are. This was after the 2011 Tohoku earthquake. And there's Professor Ishihara and Robb and Brady Cox and Clint Wood. And highlight of my life was shopping for sledgehammers at the hardware store with Professor Ishihara and debating, the merits of different sledgehammers for our noise source. So the drawbacks of doing surface wave methods is that you're capturing the dispersion curve, and then you have to invert that to get the wave velocity profile. There's movement towards just characterizing things based on the dispersion curve. Not there yet. People still want to see shear wave velocity. And so that inversion process is where things get a little bit messy, and you can have non-unique conversions. And then you argue about, oh, is there a stiff layer? Is there a soft layer? So the drawback of surface wave methods is that for liquefaction, we're trying to capture the properties of usually one layer or one region. And with surface wave methods, there's a lot of smearing. So it's an approximation best. These are just comments about doing that conversion. Passive methods, which I'm very fond of, so we're not actually hitting a sledgehammer or having a vibricize, or I don't know if you guys have seen the shotgun, the Ginnies, where the shotgun is loaded with a thing and shoot it into the ground. Here, we had a project where we're comparing all the methods that we could throw at it. This is, we're doing a linear passive array where we're doing REMI, FK, SPAC, and this was in downtown San Francisco with my grad students there. And so here's just some thoughts on passive methods, which have the same caveats as SASW and MASW, which are active methods. My personal favorite is SPAC because you're using a two-dimensional array, and it tends to have, it tends to pick up more than the other methods that I played with. FK, definitely second. REMI, the caveat with REMI is that sometimes it works, but you don't know when it's working and when it's not working. And then, I don't know if you've seen the recent movement of using fiber optic cables, and that's called DOS, that's distributed acoustic sensing. And basically, any fiber optic cable that's not currently being used, it's called a dark fiber. You can put what's called an interrogator, and you can turn a line of fiber optics into as many seismic sensors as you want. You can discretize it in any size. And there's a lot of neat applications that are happening with that right now. So surface wave testing, you measure the dispersion, you fit a theoretical dispersion curve, and then you get a velocity profile. Here's DOS, where you have a fiber optic cable, you attach an interrogator to it, and essentially you're doing the same thing, is you're coming up with a dispersion curve, and then you do the conversion. The neat thing about DOS is that you don't throw out a bunch of geophones, you're just using the cable and you discretize it as much as you want. We're doing some offshore work right now, and those are called Schultz waves, which is surface waves where there's a water boundary and geomaterial boundary, but it's the same thing as Rayleigh waves. And we're imaging the seafloor instead of doing traditional offshore geophysics. And then we get to invasive methods. Standard downhole, crosshole, seismic CPT, and suspension logging. For my money, seismic CPT is it. You get a seismic CPT rig out there and make both measurements at the same time. That's the good stuff. Here I'm showing the suspension log, which is an interesting device, often kind of expensive. You got to drill the hole and often you case the hole, and then you got to get good contact. It makes very small scale measurements from the source to the receiver. And I wanted to touch on precision and accuracy. So what methods work best and under what conditions? And the variables that we have to play with are the equipment, the methods, the site conditions, and the operators and their experience. And that last one is key. Operator and experience is key in getting good measurements. That site that I showed you before that was in San Francisco where my graduate students standing there, what we had was a dense urban environment with lots of ambient noise, and we used it as a test case. And they were excavating down 20 meters, and so every summer we'd go there and they'd be further down, and we made repeated measurements with all the methods that I've listed here, and we were trying to find out what works best in this particular situation. And we had a fiber-sized truck, and we had seismic CPT, and we did, with the fiber-sized truck, we did SASW and MASW, and then we did all the passive methods. And in that particular environment, the ambient noise was such that the active source methods even with the fiber size. We also had mobile shakers out there from the USGS. Even with those large noise sources, the ambient noise was overwhelming, and those active methods didn't work well at all. And the passive methods won out, but seismic CPT beat all of them hands down in that particular situation. So here, with this study, we tried to come up with precision. So that's the repeatability, coefficient of variation. And as you can see here, invasive methods have the best repeatability, and their seismic CPT would be the winner. And then we go down the list in terms of other methods in repeatability. You get in the middle there, 5 to 10% coefficient of variation is where you see the stack. And then we get to accuracy. And accuracy is, for invasive methods, is a function of how much soil disturbance occurs. And it's also a function of where your source is to your receiver. When you're pushing the cone, your source is always at the ground surface, and so as you get deeper, you get further away from the source, and so you have to make sure that there's good fidelity to the source. The suspension logger has the source and receiver going out at the same time, but if you have a lot of disturbance in the drilling, those waves are going through that disturbed soil, and you're not really getting the intact shear wave velocity that you're after. So accuracy for non-invasive, that's a function of the resolution and fidelity of the surface waves. One of the interesting artifacts of that site is that there were some buried foundations and other things that we found later that were inhibiting capturing the surface waves in certain locations. To inform us about this accuracy and precision, the blind studies that were, they were pretty hot and heavy in the early aughts were great. So someone had characterized the site and then invited all comers to bring their equipment and do the test and then do blind prediction. The figure on the left I'm showing is all the measurements that we made at that San Francisco site. And on the right is comparing the theoretical dispersion curves to measured data. And more blind studies are needed, but we, prior to this study, we didn't have a very good handle on accuracy and precision, and now we feel like we're getting there, and we feel more informed about the devices and the measuring techniques that we're using. So how accurate is accurate enough? Well, if we're doing site response analysis and we just need, a shear wave velocity profile that gives us the general guidelines of how the site's going to behave dynamically, then surface wave methods do a very good job. It's reasonable enough to give us good site response. For liquefaction, 10% coefficient of variation for a particular layer could make the difference between engineers deciding that they need to do ground improvement or not. And so if it's unclear, if you're doing some type of surface wave method and there's a stiff layer that's impeding those surface waves and making it up to the geophones, and you're not quite, like, there's a lot of fuzz when you go from the dispersion curve to inverted profile, then coming up with a more precise and accurate method is a better way to go in terms of seismic CPT. So some summary thoughts. Shear wave velocity against small strain stiffness is arguably one of the easiest parameters to measure. And the fidelity between lab testing and field testing, I can't emphasize enough. Again, when we're doing liquefaction tests in the lab, we learn a lot about the material, but then we have to say, well, it was this relative density, and that relative density kind of correlates to this flow count, or kind of correlates to this tip resistance. And then you add all that uncertainty into that. Whereas we measure the shear wave velocity in the lab, and we measure the shear wave velocity in the field, and it's going to work. Liquefaction and post-liquefaction be quantified relatively well with shear wave velocity. So that's not during liquefaction, but that's before and after. And we can look at both triggering, and you can look at consequences while we're measuring show velocity in our experiments and translate that to the field. Show velocity is great at aging effects, and I think there's a lot of work to be done here. Aging effects come in a whole bunch of different flavors, and it's going to be really interesting to say, for instance, calcareous soils and the bonding there, or volcanic soils where there's interlocking of the particles, and as they age, that material gets stronger and stronger, or just regular quartz sands, where they have a dense packing, and there may not be actual bonds, but that dense packing due to stress over time shows up in shear velocity. Field tests, as I've shown, have different levels of precision and accuracy, and different levels of applicability, which needs to be considered for each engineering project problem. And then the trade-offs are between time and cost. I just got back from a project up in Alaska. I took my geophones with me. I throw out a circular array. I do SPAC. It takes me 45 minutes. And then I go back and I process the data. It takes me like an hour per site. And I have a reasonable shear velocity profile. And then I also had the seismic CPT truck come up and also make the measurement, because I really needed to pin down the particular liquefiable layers for turning these cases into case histories from a prior earthquake. So the trade-off, 45 minutes, me and my geophones versus mobilizing a truck, $10,000 a day, depending on the load, and then the crew running the truck. Yeah, so it depends on the problem. And that's all I have for you today. I appreciate your time, and again, thanks for bringing me out here. I've never visited Cyprus, and it's lovely. It's great. Thanks.
Thank you very much, Professor, for the excellent presentation. I think we can have questions now.
Professor Mas, thank you. Today you gave us the opportunity to learn something, and I truly appreciate it. Two questions. One is, I would like to get your comments about shaking table tests you perform in the lab. We were very excited. It looks like the lab and the field post-liquefaction shear strength relationships are in conformance. So I'm so happy to see that. The question is, in the lab, we have low levels of stresses. As you would imagine, the question would be about, in the field, we have relatively higher confinement stresses, in the lab, lower, and we know that there's non-linear relationships. I would like to get your opinion on that, how to tackle that problem, or should we just ignore it?
With that, you didn't see that, but with that, we call it our bucket. We actually had a top cap on it, and we pressurized it. Right now, I can't recall what stresses that we were able to achieve, but we didn't, surface liquefaction is not a thing. You're not going to liquefy a soil that's not confined a little bit. And so that's what we were after, is we're after some confinement so that we could get down to a sweet spot. And yeah, so getting the stresses right is tricky. And like I was just visiting UNR, Reno, Nevada, and they have two large shake tables, and they just assembled a brand new laminar box that's, gosh, the thing's huge. It's probably 5 meters tall, maybe a little taller than that. And the same thing is they have a top cap, and they pressurize it to try to mimic some of those surface stresses pushing down. So that's always the trick. When you compare to centrifuge, right? Centrifuge, you can mimic the stresses right, but then you have these little tiny CPT toothpicks in there, and then we often question the results in terms of the similitude of the fluid behavior and the deformation properties. So there's no, what would be ideal? We have one of those T-Rexes and we have sites all over the place and we have tons of money and we instrument sites and we go around and liquefy them, right? Wouldn't that be great? Is we have all these candidate sites. If you have a site and you know that there's going to be liquefied material and you're going to have to do ground proofing. What if we got a mobile shaker out there, stuck some accelerometers and pore pressure transducers in the ground and shook it before we did the ground improvement? If we did that regularly, we wouldn't need centrifuge or shake table tests. So that was question one.
Thank you so much. Actually, I'm glad I asked that question because it's obvious that you apply some cap stresses to basically eliminate that problem. The second question was about ship rate velocity measurements with invasive and non-invasive methods. It looks like we need to standardize it for engineering purposes because the differences could be significant, as you very well presented. As we have standardized SPD and CDs,
Yes.
would you recommend a standardization for ship rate velocity measurements?
We have colleagues that are working on it right now. Fody, who's in Europe, and Brady Cox, who's in the US, have been working for years to try to come up with some standardization. In order to standardize, you have to be able to quantify the uncertainty in a very standard way. And that's one of the tricks with the surface wave methods is what is a reasonable uncertainty band for a given set of conditions and what is operator error and people just not doing it right. And they're getting closer, but it's not there yet. There's some preliminary standards that they've been working on, but trying to say this is the known unknowns and then this is garbage is the tricky part. Discerning between what good surface wave method tests look like and practices are versus someone who doesn't have the expertise, that's the tricky part right now. And you probably noticed I'm not a big fan of REMI because REMI is a wild card. Sometimes you'll get good REMI results and sometimes you get what look like good REMI results but turn out they're bad and you don't know when they're good and when they're bad. So there has to be that loop that closes in terms of the testing, you're getting good data and you're able to do an inversion with a minimum amount of epistemic uncertainty that we've introduced into it. Thanks for the good questions.
Hi, Professor. Thank you for the wonderful presentation. Again, my question also about shear wave velocity measurements in the lab. There is two types, as far as I know, using accelerometers and piezoelectric elements. What is your insights about the advantages and disadvantages of each of them?
I've used both. And honestly, the piezo crystals and the bender elements come from the manufacturer, and it's a black box. Like the box in my lab is black, and you turn it on, and you say go, and then it captures the shear wave velocity and says, "Here's your velocity." So it being a black box, and me not having created that system myself, I can't really comment on that too much other than it gives a value and it looks reasonable. It's between 100 and 300 views per second, and if it's a dense sand and it's giving me like 230, I say, okay, that's good enough. Whereas when I showed the medium scale where we actually have the accelerometers and we wrote the LabVIEW code that captures it, and then I wrote the script that processes it, there I feel really good about it because I'll do the test repeatedly and I am generating the signal. I actually have a block of wood. It turns out, and we've done this a bunch, we did it with a whole slew of different types of tests. A block of wood and a rubber hammer works the best. We tried everything. Metal hammers, hitting metal, big hammers, big mallets, small hammers, small mallets. block of wood and a rubber hammer gives us the cleanest signal, and there I have confidence in it. So I can generate the signal, I know how we're capturing the signal, I know how I'm processing the signal, I'm picking up the, the first in both the accelerometers, and then I have confidence in that. So for my money, that's where it's at. But then when we're talking about triaxial, or we're talking about a simple shear size, that's actually, the accelerometer is getting really small. So you could build a system like that, but it's often easier just to purchase the ultrasonic patents from the company and say, okay, black box, tell me what's going on. So with a torsion shear, you might be able to get some of the small accelerometers in there yourself, because I know you guys are manufacturing the equipment. So, great question.
So one simple question. I know measuring wave velocity is a little bit hard, but with a very small height sample, did you able to achieve it? And would you, if you compare it with the longer sample, does it make a difference? I mean, measuring it with a simple shear, the height of it might be.
Well, when we're in the lab, we're creating the samples. So when I showed the slump test, we've got, I spaced the accelerometers 5-7 centimeters, but I've created the sample. So I've created a loose, consistent specimen, and that distance, it doesn't matter. Unless I have a variable density in the material, then it's going to give me accurate measurement. In terms of picking out the signal, like that's just the sampling rate. So we're running at 1,000 hertz sampling, and that's enough to, and most run-of-the-mill data acquisition systems can do that, and then it's easy to pick up the first arrival and the 2 accelerometers.
Thank you.
Thank you.
Thank you.
So, in order to express our appreciation, I would like to invite Professor Kemal Önderçetin of Middle East Technical University to present Professor Mosley's slide.
Full disclosure, Honor and I go way back.
Yes, and last, thanks for joining us. There was actually and then
Now we'll carry on with the next presentation, which is on granular liquefaction cases. So exactly